That's why I just logged out. Okay. So I welcome you again in the live interaction session for the course Introduction to Rings and Fields. So this is the third interaction session, and we are going to start with the question that says that each maximal ideal in a ring is also a prime ideal. So here, as the course demands, by a ring we always mean a commutative ring with unity. So yes, I hope that this has already been discussed in the class notes as well in some form, but let's discuss it formally. So is there any input from your side? You want to say something? Because I think this is easy and you might have seen some kind of proof of it in the class notes as well. So I'm assuming that you have gone through the notes and you know the definition of maximal ideal and prime ideal. So is there anyone who wants me to repeat the definition?
Maximal ideal is an ideal which is not equal to R, the whole ring, yes. And it will not allow any ideal properly sitting between R and this ideal. So
yes. So let me just build up on your comment. Thanks, Muthu. So as he said that ideal is an ideal. Let's say I'm denoting it with I, which is not equal to R, is said to be a maximal ideal of the ring R if for all ideals J such that it is between, say, I and R. You always have we have either I is equal to J or J is equal to R. So whenever you get this kind of condition that some ideals satisfies this, that it's contained I and it is an ideal of R, then that ideal is either equal to I or it's equal to R. So there is nothing between I and R. Okay. And so prime ideal also, I hope you guys know already. So can one person just say it, what it is? It's just for revision, right? So I hope you all know it.
An ideal I is the prime ideal if AB belongs to I, implies either A belongs to I or B belongs to I.
Yes. So as the prime numbers do for integers, that if a prime number divides a product of numbers, then it has to divide one of them. Similarly, through the same intuition, we define an ideal to be prime if whenever you have AB belongs to I, either A belongs to I or B belongs to I. Okay. So now what we are supposed to prove that if something is a maximal ideal of a commutative ring with unity, then it's also a prime ideal. Okay. So Now this is just the recall part. Now, is there any input from your side how we can prove this? So let's say I be a maximal ideal. Okay, then what we need to show? We need to show that I is prime. Okay, so let AB are some ring elements such that their product is inside I. So how one can proceed to prove that one of them is also one belongs to I?
Assume A not in I.
Okay, so uh, assume that A is not inside I. Then we have to show that B is inside I. And how to do that? Definitely we have to use the fact that I is maximal.
So
So
we
for
need to define an ideal J
okay, define.
such that I is contained in J, J is contained in R.
Yes.
J is
So
always contained in R. Only thing I contained in J.
so see, A is not inside I. So if we define something that contains I and A, then that ideal has to be the entire ring R by the maximality of I. That you agree? Because I is a maximal ideal. If some ideal that contains I and one other extra element, then that ideal definitely cannot be I. But as I is maximal, so if something contains it properly, then it has to be in the entire ring. Okay. So we have to define J in such a way that J contains I and it's some other ideal. So I, sum of ideals you have already seen, I plus some ideal that contains A. So the natural choice
Ideal,
is,
ideal generated by B.
yeah, ideal generated by A, that is AR. Okay. Or at some place, this is also denoted by just say this bracket of A. That means the same thing, that this is the set AR such that R belongs to R. Okay. So as this is a ring with unity, so you can take R to be 1 and then A belongs to this set AR, and so uh, I is contained in J. Okay. Uh, because any element if you take from I, you can write it as I plus A times 0, that is inside J. So I is always contained in J, and 0 plus A times 1, that is A, is inside I plus AR, and that is J. So J is such that J contains I and J also has A. Okay. Now since A is not inside I by our assumption. Okay. This is our assumption. So by the assumption we have that J properly contains I. Okay. Now by the maximality of I. Now by the maximality of I, we have J to be the entire ring R. Okay, because whenever you have this kind of condition, I contain in J, contain in R, if either you have I equal to J or J equal to R. But here already this condition is not there because J properly contains I. So what's the other option? That J should be equal to R. Okay, so that's following by the maximality of the ideal I. This trick is very common while dealing with results related to maximal ideals. Just uh, uh, have a look at it again. So whenever you are given a maximal ideal and you are supposed to prove something related to it, the most common trick is you generate an ideal such that it properly contains the ideal. And then as the previous ideal is maximal, so the new ideal is going to be the entire ring. So for that, you just find an element which is not inside I and then define J to be I plus the ideal generated by that element. And this new ideal has to be equal to R due to the maximality of J. So we have J plus AR to be equal, same as R. Okay. So till now, that's what we are able to show. Okay. Now, what? So once you got this, then again, step that I'm going to write that you will see very often while having a look at this kind of condition. The first thing that comes to mind is if this is the case, then definitely we have, so one is inside R, right? Since one is inside R, you have one belonging to J plus AR as well. Therefore, one belongs to J plus AR. And what does this means? This implies that there exists something inside, say J inside J and R inside R, such that your element 1 is J plus AR. Okay. So till now, do you have any doubt in that, or it's okay? Oh, I just did a small mistake. So J is equal to I plus AR. So we have J equal to R. That means this is I plus AR, not J plus AR. This I plus AR is J. Let me just write. Okay, so we have J plus plus. Sorry, again the same mistake. It's I plus AR. So there I just say S in I and R in S, as that one is S plus AR. Okay. So this step is also common in most of the proofs of maximal ideal. So in most of the theorems related to maximal ideal, the key part is to construct this J using an element that is not inside I. Once you did this, these steps are followed for each and almost every result related to maximal ideals. So what we have 1 is equal to S plus AR. Now, this implies that when you multiply it with B dot 1, that is B dot S plus AR, use the distributive property of the ring. You have BS plus BAR. Now here you have to use the commutative part that the other term BAR is same as ABR. Now S is there inside I. Therefore, B times S is also there inside I. And we already have AB let me write here only. AB also inside I by our assumption. Okay, that AB is inside I. So then what? The other term, that is AB of R, that is also there inside I, and thus there's some BS plus AB of R is also inside I. But what is this? This is B. Okay, so we have B is inside I. So that's what we are supposed to prove, right? We take the product of two elements AB. We assume that, let's say, the first one is not there inside I. Then we prove that if that is the case, then the second one will always be there inside. We have established the claim that it's a prime ideal. Okay. Now the obvious question comes that what about the converse?
Converse is not true.
Yes.
If converse is true, then there is no point in defining prime ideal and maximal ideal separately.
Yeah, but it might happen na, that this is true only when you are having commutative rings with unity.
So is it is a ring?
Yeah, good.
In which zero is a prime ideal but not a maximal ideal.
Good. So yes, you are right. The converse is not true. Take R to be Z and I to be the zero ideal. Then I is prime, but not maximal. Okay. So that you can see easily that why I0 is a prime ideal and it's not maximal. So for maximal, definitely I is contained, properly contained in say 2 of Z, and that is not equal to Z. So this implies that this is not maximal. And for prime, you all know that Z is an integral domain as well. So whenever say AB belongs to I, that is 0, that implies that AB is equal to 0, and that implies either A equal to 0 or B is equal to 0. Thus, A belongs to I or B belongs to I. So I equal to 0 is a prime ideal. Now, can we impose some other conditions over the ring so that each prime ideal also becomes a maximal ideal? Yes. If we have commutative rings with unity, there it is not true. So let's say I put some more conditions, whether maximal is same as prime. So is there any such condition? So that's so the next question is about that only. Let me just write the second question, and I am expecting the answer from you guys because whatever is required to solve that you already know. So it's all about collecting the facts and then saying it. So if R is a finite ring, or let me just specify it's a commutative ring with unity, then an ideal I of R is a prime ideal if and only if I is a maximal ideal. So if you are in finite setup as well, then both rings, both the cases are just same. Yes. So uh, yes, what your take on that? Can you just help me in saying why it is so? You know already all the things that are required to prove this. There is nothing new that I'm going to use. It's all about collecting the facts and then just saying it aloud. Yes. Any inputs? Divya, you want to say something? Muthu has already helped us in proving the first solution. So, uh, Divya, we want to give the first chance to you. No? So, yes, Muthu, you want to say something?
Every finite integral domain is a field.
Yes, very good. Then how
So,
we can use it?
because we have already proved now that every maximal ideal is a prime ideal. So we need to prove only the converse. Prime ideal implies maximal.
Yes.
When I is prime, R by I is an integral domain.
Yes.
Since R is a finite one, therefore that R by I is a finite integral domain, which is a field. When R by I is a field, I is maximal.
Yes, very good. So we know that every finite integral domain is a field, right? And we are just going to use it. So uh, for commutative rings with unity, we have uh, an ideal I is maximal if and only if R by I is a field, and as we are in finite setup, so this is going to imply if and only if, since R is finite, therefore R by I is also finite, and thus R by I is a field if and only if R by I is an integral domain. Okay, and that's going to happen if and only if you have R by I to be a prime ideal. Okay, so yeah, that's it for finite setup. And of course, in commutative rings with unity setup, you always have these four things to be same. Yes. So I hope this is clear. Let me just move on to the next question. Actually, the next question, in the next question, I was supposed to prove uh, these things. So let me just show these implications. Okay, so let me just write it part 1 and it to be part 2. Okay, so this part is anyway, I leave it to you that every finite integral domain is uh, field. So this is as an exercise. I am leaving it to you. Okay, but it's good to see part 1 and part 2. So proof of first part. So we have to show that if I is maximal if and only if R by I is a field. Okay. So let us assume let I be a maximal ideal of the ring R. Then we need to show that R by I is a field, right? Yes. So we need to show R by I is a field. So first of all, it is clear that since R is a commutative ring with unity, therefore uh, we have R by I also a commutative ring with unity. So what is left to show that? So it is enough to show that each non-zero element of R by I has multiplicative inverse. Okay. So how to proceed then? So let us assume that A plus I belongs to R by I such that A plus I is not equal to I. Then what we can figure out from this? Yes, Muthu, you want to give some inputs?
A not in I.
Yes, definitely is not in I. Then the same trick we will do, right? As we did in the first question. So we can define J as we defined earlier as A plus I plus AR such that I is properly contained inside J, and definitely A is also inside J, right? So by the maximality of I again, the same thing we will do, right? So by since I is maximal, therefore we will have J, that is I plus AR, to be same as R. Okay, and now what's next? We need to show that A plus I is invertible inside R by I. So obvious step after that is we know one belongs to R. Therefore, there exists some element, again go with the same notation, S belongs to I and R belongs to R, such that one is S plus AR, just a repetition of the previous step. Now we have to change a bit. So this is inside I, right? This S is inside I. So just keep this. So what we have, this implies this element 1 plus I is what? This is S plus AR plus I. Okay, and that means that it is S plus I. Now, if you are looking at addition in R by I, this is A R plus I, right? And S plus I is nothing but the zero of R by I, because this element is inside I, right? So this is just 0 plus I, you can write. And this can also be written as A plus I and R plus I. Okay. Now what? This is 0, so when you add it, you are just supposed to get A plus I and R plus I. So what you got? You got that 1 plus I is A plus I times R by R plus I. Thus, A plus I is invertible in R by I. So the first thing is okay, that we have R by I to be a field. Okay, so now the other implication we have to check. So this is the proof for this direction. Now I won't say much in the converse direction, because I hope that's not difficult. So let I be an ideal of R such that R by I is a field. Now we uh, uh, will show that I is a maximal ideal of R. Okay. So, yes. Muthu, you want to give some inputs?
Any field has only two ideals.
Yes.
Zero ideal and the whole field.
Yeah.
So R by I has only two ideals.
Yes.
One is I, the other one is R by I.
I and R by I. Good. Then
Therefore, you cannot have any ideal which properly contains I and properly contained in R.
yes. Mm, but we have to then show that that ideal is I or R. Yes. So one thing is you use the correspondence thing. I think you are just about to say that. So um,
For the previous part also, then you can use the correspondence theorem.
yes, yes, yes. But I was not actually hoping to use that, because some people might not have seen the that correspondence thing, although it's already there in the notes. So without using that, just by the definition also we can prove, right? So definitely first uh, method is one can use the correspondence theorem relating the ideals of R by I to the ideals of I in R that contains I, or by the definition also we can see that I is a maximal ideal of R. Now how to do that? So there's nothing much. So let J be an ideal of R such that I is, let's say I'm assuming it is not uh, equal to R, I, then we will show that J is equal to R. Okay. So since I is properly contained in J, therefore there exists some element in J such that uh, that element is not inside I, right? And that implies that this element A plus I is not equal to I. But what is I? I is the uh, this is not write this. This is 0 of R by I, right? So since you have uh, R by I to be a field, therefore uh, A plus uh, I is invertible, and so there exists some B plus I inside R by I such that B plus I times A plus I is equal to 1 plus I. Okay. Yes. So what does this imply? This implies that BA plus I is equal to 1 plus I. And thus you have 1 minus BA is uh, inside I, right? So till now it's okay. And I is contained inside Z, in fact properly J. So 1 minus BA belongs to J. And also we have assumed that A is there inside J. This implies that 1 minus BA plus BA, uh, that is also inside, that is also there inside J, right? And if I one is there, then that has to be the entire idea. Okay. So without using the correspondence theorem also we can prove that just by the definition. But of course, if you know the correspondence theorem, then also this is fine, that if R by I is a field, then there are only two ideals of R by I, that is I and R by I. So it has to be in one correspondence with the ideals of R that contains I. There are only two ideas that contains uh, I inside R, so that is I and R. There is nothing in between that. So from there also directly you can say that whenever this holds, whenever R by I is a field, then uh, I is a maximal ideal. So, but if you don't want to use that, then without using that also you can uh, also show that I is a maximal ideal. Okay then. So now the second part. So for second part, one has to show that something is uh, a prime ideal if and only if its quotient is an integral domain. So here I did a mistake again. So R by I is an integral domain if and only if I is a prime ideal. So let us prove the first implication. I won't say much, but let me just write something. So we will show that if R by I is a integral domain, then I is a prime ideal. So if R by I is an integral domain, then we will show that I is a prime ideal. Okay. So in fact, I think we can do both things parallelly. The if and only we should try to prove the if and only part in one go if we can do. But let's go with the one implication for a time to not increase the confusion. So let's say there are two elements in I. Okay, then what you have AB plus I is going to be I, which is the zero of R by I. So since you have R by I to be an integral domain, that is going to imply straightforward thing that a, okay, so this is nothing but, let me just write one more step, A plus I times B plus I. Okay, so this implies A plus I is equal to I, or B plus I is equal to I. And this is because R by I is an integral. But that is that will imply that A belongs to I or B belongs to I. Okay, so that's not difficult to see. I hope that is clear. If you have any doubt, then you can ask. Otherwise, I will just quickly say the other implication and then move to the next question. If you have any doubt in any step, then just stop me in between. I will explain it again. Okay, so here we will prove that I is a prime ideal, implies R by I is integral domain. So that what we will show now. So let uh, AB plus I belongs to R by I such that AB plus I is the zero of uh, R by I. Okay, or
AB,
let me.
AB plus I.
Oh, yes, yes. AB belongs to I have written. Okay, or let me write it more clearly as a product of two elements. So A plus I. Let me just rephrase this entire line again. Yeah, thank you, Muthu. So let uh, A plus I and B plus I is inside R by I be such that you have their product getting equal to the zero of the ring R by I. Now this will implies that AB plus I is equal to I, and that will imply AB belongs to I. Now since I is a prime ideal, I'm a bit quick because I think these all things you might have seen in the notes. But let me just for the sake of revise, I am repeating these things. So A belongs to I or B belongs to I. Okay. And so that will implies that A plus I is equal to I or B plus I is equal to I. And these are the so I is zero of the ring R by I. So that's why this implies that R by I is an integral domain. Okay. So yeah, now with all these facts, we can say that whenever you are in a finite setup, you have prime ideal same as the uh, maximal ideal. And these intermediate steps that we proved, that is true for any commutative over any commutative ring with unity. For that, you even don't need I R to be finite. Okay, so just uh, as a note, I'm writing first and second don't require R by I to be finite. Okay. Okay then. So let me just try to solve now some interesting problems. We have been doing these things, some revision of the class notes and some related things for a while. So let me just now start with some uh, interesting problems. So question 4 is, if uh, R is an integral domain, then every unit element in Rx, that is a polynomial ring in one variable over the ring R. So every unit element in Rx must be a unit element in R. Okay, so some polynomial is a unit element in Rx, that has to, then it has to be a unit element in R. So first of all, that implies that it's an element of R. So the variable part is 0. Only you have constant part, and that also a unit in R. Okay, so over the integral domains, the units are well defined, and they are just the units of the ring R. Yes. Yeah. Does any one of you want to say something? How to proceed with that? So let's say that let fx belongs to Rx be a unit in Rx. Then first there exists uh, Gx in Rx such that fx times Gx is 1. Okay. Now, if fx is a naught plus say a1x plus dot 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 an xn, and gx is b naught plus b1x plus dot 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 bn xn, then what? So okay, so instead of if, let me say let also let a fx is this and gx is this. So now what you can say? See, since you are in integral domain setup, we can compare the degrees of both sides. So let me just write it here. From here, what you will get? You will get uh, degree of fx dot gx is same as degree of the polynomial 1. But what is the degree of this? It has degree 0, which implies, and this degree is also same as the degree of fx plus gx. In these calculations, we are using that the underlying ring is an integral domain. Okay, so this is 0, and since degree is always positive, degree of fx and degree of gx, this is always greater than equal to 0. Therefore, we have degree of fx to be equal to 0 and degree of gx is equal to 0. What does this implies? This implies that fx is just a naught and gx is nothing but b naught. So they are just the scalars, the elements of the ring R, and which implies since we have fx gx equal to 1, so a naught b naught is equal to 1, and thus fx is equal to a naught is a unit in R. Okay. So yes. So whenever you are in integral domain, then the polynomial rings over it has units, precisely the units of R. So their units are the same. But what about on an arbitrary ring? For an arbitrary ring, this won't be true in general, but again we can say something, and for that let us just first try to see some observations, and then we will see that what are the units for the polynomial rings over arbitrary rings. Okay, so our next uh, two questions, or the three questions will be in the direction of looking at the units for arbitrary rings. So for units over arbitrary rings, we will solve the next few exercises. So does any one of you know how units over an arbitrary ring look like? Arbitrary polynomial ring, Rx. Muthu, have you seen that thing before? Okay, if not, then let us see it together. Yeah, you want to say something?
You can be more specific that where we have used that R is an integral domain.
See, for this degree kind of calculation, we need R to be an integral domain, first of all. So this idea of degree, we won't be using over arbitrary commutative ring. That's the difference. Okay. Okay. So yes, let us then proceed towards the next exercises. And our aim, you all know, that will be to specify the units in Rx. So first of all, an easy exercise. Let xy belongs to R are nilpotent elements of the ring R. Then x plus y is also nilpotent in R. Yes, so that should not be a problem, I think. Uh, you can see this. I will be happy to have inputs from your side because that's not difficult. Yes, anyone?
So x power m equal to 0, y power n equal to 0. Consider x plus y whole power m plus n.
Yes. Good, Muthu. So since x and y are nilpotent element are nilpotent, therefore there exists some m in n and n in n such that x raised to m is 0 and y raised to n is 0. And since we are in commutative setup, so we can use the binomial expansion. So let me just write in commutative rings with unity, we can use binomial expansion. Therefore, x plus y raised to m plus n, we can just use binomial expansion. So it is nothing but nc 0 x raised to m plus n plus nc1 x raised to m plus n minus 1 y1 dot n c n minus 1 x y m plus n minus 1, and then at the end you have ncn y raised to x plus m. Oh, y raised to m plus n. Now from here, how can you conclude that this is 0? So just to make your life easy, let me write it as in summand form. So it is running, it will be running from I equal to 0 to n mci x raised to m plus n minus I y raised to I. Now can you just say it quickly why this sum is 0? Yes. No. So see, you have to use that x raised to m is 0 and y raised to n is 0.
I equal to 0 to m plus n or n?
Yes. Thank you, Muthu. Yes. Okay. Now can you say this? It's a one-liner.
Up to 0 to n x power m is 0.
Yes.
So we can split into two summation. 0
Yes.
to n plus 1 to n plus m.
Yeah, that also we can do. It is 0 to say n mci x m plus n minus I y I plus summation I equal to n plus 1 to n plus m mci x raised to m plus n minus I and then y of I. Yes. So this part is going to be 0 since x raised to m is 0 and this part is going to be 0 since y raised to n is equal to 0. So all some terms here has powers of y as greater than equal to n, sorry, strictly greater than n. So this is going to be 0, and here all terms has power of x greater than equal to m. So this part is also 0. Okay. So Thus, the sum is 0, and which implies x plus y is uh, nilpotent. So can we say that nilpotent index of x is m plus n? No, right? Because this is happening for some m plus n, but in general we can have a number smaller than m plus n also, for which this satisfies. For example, you can just take uh, y to be minus of x. So if x is nilpotent, minus of x is also nilpotent, and their sum is anyway 0. So for that, even n plus m is equal to n plus m is 2n, that is strictly greater than 1. So this number can and its nilpotent index can be smaller, but that we don't need to worry. We just need to show that for some number it's working. Okay, so let me just write the next problem. If you have any doubt in this, then you can just ask. We just prove that if x is an important, y is an important, then x plus y is also an important. Okay. Okay. So question number 6. So it's again related to important elements, but here we also have unit elements coming into the picture. So let R be a ring. Okay. U be a unit in R, and X be an important element. There is some disturbance. Let me just mute him. So Jnana Prakasham, can you just mute yourself? I have to mute him. Okay. Okay, so let's get back to the question again. So what I'm saying, R is a ring and U is a unit in R, and X is also an important element in R. Then what you want to say about U plus X? U plus X is an unit in R. So the sum of a unit and an important element is again a unit. Okay. Yes. How to proceed with that? So let's first collect what we have. Since U is a unit in R, therefore there exists some V inside R such that U times V is equal to 1, right? So that is the first thing. And since X is a nilpotent element in R, therefore there exists some natural number in N such that x raised to n is 0, right? So now how can you find the inverse of u plus x? So just consider this thing. Consider, say, what notation I should give? Y maybe. So have a look at this particular element of R. V minus V square x plus V cube x square minus V4 x cube dot minus 1 raised to k minus 1. Yes, and I have V to be V raised to k x raised to k minus 1. This particular element will work as a inverse of u plus x. So then what is u plus x times y? You can check that u plus x times y is nothing but this expression v square x v cube x square it's not like that this expression in expression is coming from nowhere. There is some motivation behind that. I will tell you why what's the motivation, but let us first see that it is actually the inverse of u plus x. Okay, so I will multiply this expression in a particular manner that for each element in the right hand side, I will first multiply it with u, then x, then I will move to the next term, I will multiply it with u and then x, and so on we will do it. Okay, so what u v plus x v minus u v square x plus uh, x v cube, uh, sorry, plus, so I multiplied uh, u plus x with v, and then I am multiplying u plus x with the second term v square x. This is minus of v square x square, and then we have plus u v cube x cube plus v cube u v cube x square, and then we have v cube x cube. Okay, dot. The last, at last, what we will get? We will have minus 1 raised to k minus 1 u v k x k minus 1 plus minus 1 raised to k minus 1 vk xk. Okay, so that's what we will get. Now there will be cancellations. So uv is 1. Okay, so we have 1 plus xv. Again uv is 1. So what we have, what you have, vx, right? This is uv times v, that is uv is 1, so we have vx minus v square x square. You can, uv is 1, so what you have, v square x square, and then so on. You will proceed and see that there will be cancellations. Dot. At the end you have minus of 1 k minus 1 v of k minus 1 xk minus 1 plus minus 1 of k minus 1 v of k xk. Okay. So there will be cancellations. Since we are in competitive setup, we don't really worry about XV and VX. So these will get cancelled. Everything will get cancelled. So this term will get cancelled by something before it. Okay. And only this term and this term will survive. So you have 1 plus minus 1 of k minus 1 vk xk. But this term is 0. Why? Because you have, let me just, so I use here n and there I'm using k. That's not a good thing. So let me just use the same notation k. Okay. So as xk is 0, so this term is 0. So we are left with only 1. Okay. So this implies that y is the inverse of u plus x, and thus u plus x is a unit. Okay. So if you have an important element and a unit, then their sum is always a unipotent element. Unit. Okay. The sum of a unit and an important is a unit. So as I said that this expression is not coming uh, from, it's not like that it's coming from nowhere. See, what it is, you want to find an expression for y, right? You want u plus x, y to be 1. So y is nothing but 1 upon u plus x. So in complex, you can express this function u plus x inverse, and that is precisely this. V is just u inverse, right? So you can see this, that this expression u plus x inverse will be what I have written here. Consider V to be u inverse. So it's because we want our y to be an inverse of u plus x. That's why this expression, the expression of u plus x inverse is, we want to be of this kind. And to guess that, you can just try to see how it expands. This function expands. Okay. Of course, it's an infinite series u plus x inverse. If you expand it through Taylor's expansion, uh, but as your x raised to k is 0, so you are left with finitely many terms only. Okay.
Sum
Not
to
Taylor,
n
Lorentz.
terms of GP, geometric progression, geometric series.
Uh, yes, you can also see it as a geometric progression. 1 plus a plus the extension of this 1 upon a plus r. That also you can see. But what I want to convey, that this is not, it's not like that it's coming from nowhere. It has something in the middle. Okay. The idea is we want that after multiplying it with u plus x, you just have 1. Okay. So you have we have seen in question 5 and 6. So in 5 we saw that the sum of two nilpotents is an nilpotent element, and then in 6 we saw that the sum of a unit and a nilpotent is again a unit. Now using these things, we are in position to uh, solve the next exercise, which will give us the all units in and for a polynomial ring over a commutative ring with unity. Okay. So let me just write, let fx is equal to, say, a naught plus a1x plus dot 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 an xn belongs to the polynomial ring Rx, then fx is a unit in Rx if and only if first thing is a naught is a unit in R, and the second is the elements A2, A3, oh, sorry, A1 also is there. A1, A2, dot, 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 AN are nilpotent elements of R. Yes. So we have a complete description of units for a polynomial ring as well. And it says that some polynomial is a unit if you have the constant term to be a unit in the ring, and the constants of the and the multiples of these variable terms. These are just the nilpotent elements of your ring. So, and this is an if and only if statement. Okay. Yes. So what's your guess? Which part is going to be easy? The forward implication or the backward implication?
Converts looks easy.
Yes, good. Yeah, so can you say something about its proof? You may use the solution 6 and solution 5.
Something to do with the maximum of the nilpotency of those A1 to AN.
I don't think that it is even required. See, in 5, what we prove that x is nilpotent, y is nilpotent, then x plus y is nilpotent. Then 6, we prove that if something is unit and we add an nilpotent unit element to it, then it still remains unit.
First, you want to prove if part or only if part.
Whatever you think is easy. Yes. If you ask me, then I will say that this sufficient part is easy. If you have A naught to be a unit and A1 to AN are important elements, then fx is a unit in Rx. That seems to be easy to me, and it follows uh, from 5 and 6. Yes. Shall I start writing?
Okay, proceed, please.
Okay. So see, uh, so I'm going to prove this first, right? So if A1, A2, dot, 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 AN are nilpotent elements of R, then can you just see this immediate observation that A1x, uh, A2x square, A3x cube, dot, 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 ANXN are nilpotent elements of Rx. First thing, this is because say if say AI raised to some ki is equal to 0, then what it is AI xi, this element, if you raise it to 0, sorry, with the power ki, what it is? It is nothing but AI power ki, and then you have x I times ki, right? But this constant term gets 0. So this entire term will be equal to 0, right?
That commutativeness help us.
Yeah, that's why I said that this is a description for commutative rings. So now you are getting the point, right? Why we have a very rich structure over the commutative rings. Because you can build so many nice results if you are in commutative ring setup, right? You have the complete description of units in our over for the polynomials in commutative rings. Okay, good. So these are nilpotent elements of Rx, right? And also now what? By solution 5, we have that their sum is also a unipotent, sorry, nilpotent element. Just applied 5 again and again. This, and xn is nilpotent element of Rx, right? And since A naught is a unit in R, and R is contained in Rx, right? Therefore, you also have that A naught is a unit in Rx. Because if you have something in R that is after multiplying with A naught giving you 1, then that's going to be the inverse of A naught inside Rx as well. Na? Is a unit in Rx also. Now apply this solution 6. You have some nilpotent element and you have some unit. So if you take the sum, then that's going to be unit again, right? Yes. That is precisely your fx. This is a unit in Rx. Okay. So one side is okay. What about the other side? Other side requires something, some tricky steps to follow. So that I will do. No issues. So let us first assume that fx is a unit. Let fx be a unit in Rx, then uh, there exists Gx is equal to, say, b naught plus b1x plus dot 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 bnx. Yeah, its degree might be different. So let me write bm xm. Okay, they might not be of the same degree, of course. So there exists Gx equal to this belongs to Rx such that fx Gx is equal to 1, right? So, but what does this means? This will implies that you have a naught plus dot 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 an xn after multiplying it with uh, not g naught, I'm writing it b naught plus b1x dot 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 bmxm, that is equal to 1, right? Let's say that this is equation 1. Now just compare the constant part. Compare the constant term of left hand side and right hand side. What you get? We get a naught b naught is equal to 1, right? This is going to be the constant part here. You agree? But that will imply that a naught is a unit in R. Okay. Now the interesting thing is to prove the other uh, condition, that A1 to AN are nilpotent elements of R. That's not straightforward. So it will actually use some kind of induction. And so that I will do. But if you have a problem at any step, then just let me know. Okay. So this is the first condition. Now for second condition, what we will first do that say by equation 1, what we have? We have uh, say after multiplying it, you will get a polynomial of degree xn plus 1. So let's say you have the polynomial to be like this, dot dot dot, you have c n plus m, x n plus m is equal to 1, where what are these c j's? So c naught is definitely a naught b naught. C1 is what? C1 is going to be, if you compare them, then it's going to be a naught b1 plus a1 b naught, and then C2 is going to be a naught b B2 plus A1 B1, and then you have A2 B0. So continuing like that, you have C of M plus N minus K is nothing but A. So their indices must add to give you the index of C. Okay. So 0 plus 1 is 1, 1 plus 0 is 2. 1 plus 0 is 1. So here also 0 plus 2 is 2, 1 plus 1 is 2, 2 plus 0 is 2. So that I think you have already seen. So we will start with A0. So A0, the index of B should be M plus N minus K, and then A1 B M plus N minus K uh, minus 1, and then dot 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 dot, you will end at A M plus N minus K and then B naught. Okay. So and if you compare them, so on to, you will go to till C of M plus N, and that is going to be AN BM, right? There is no other choice for it, because you can't extend the coefficient, the index of B to M plus 1, and you don't have here also AN plus 1. So that's it. So after comparing it, so on comparing these coefficients, with the coefficients of with the coefficients of the constant polynomial 1, what you have that. So this is, so C M plus N minus K is the coefficient of X M plus N minus K. So all these are going to be 0 except the first one, C naught. So that we have already used, that C naught is A naught B1 is equal to 1, and you have C of M plus N minus K is equal to 0 for all K belonging to uh, 0, 1, dot 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 up to M plus N minus 1. Okay. When you put K equal to M plus N, you will just get C naught. So this is 0, right? But am I mixing up something? Just give me a second. Yes. So this you have got, right? Now what is C M plus N minus K? That you know from here, that this is A naught BM B M plus N minus K, and this thing. So there is one claim that I am going to establish first. So claim is A N J plus 1 B M minus J is going to be 0 for all J between 0 and M. Okay. So this thing we will see first, and we will use this part to prove this. So uh, the obvious thing is to work with the induction proof of the claim. So for m equal to 0, sorry, for j equal to 0, what this expression is? Yes. If you put j to be 0 in this expression, then we will get an raised to 1 and bm minus 0. So this is uh, nothing but we have an bm, and that we know that it is 0, right? That is nothing but c n plus m, and that is 0, right? N plus n or m plus n both are same. So we can start our reduction from 0, right? So so for natural numbers, induction starts from 1, but for the cases like that, 0 and m, where j is increasing at each step by 1, then you can also start with j to be 0, and then assume that it is true for some j equal to I, and then establish it for uh, I plus 1. Okay, or assume it for j equal to I minus n, and then I minus 1, and then establish it for j equal to I. So let it be true for all I, uh, for all j uh, less than equal to I minus 1. Okay, so now we will show that it is true for j equal to I as well. So what's the expression that you are going to get for j equal to I? So before going to that, you have C of n plus m minus I is equal to 0, right? Because I is less than equal to m, right? So this term is not C naught, so it's 0, right? But what is the expression of C n plus m minus I? This was nothing but a n b m minus I plus a n minus 1. I started there from a naught, I guess. Let me go check. Yeah, I was starting from a naught. Let us be consistent with the notations. So this is nothing but a naught b n plus m minus I plus a1 b n plus m minus I minus 1, and then you have is it okay? Or I'm doing something silly here. I think it's okay, right? Yes. So this is A2. So let me just write the final term directly. So this will go till A N B O. Let me. This is not going to be more than. This term is not going to be more than m. So we cannot start it from A naught. We have to start it because B can go at max till M. So we cannot
Let
start
it
it
be
from.
true for all j less than or equal to I minus 1 or I.
Yes, yes, of course, yes, I minus 1. If it is true for I, yeah, thank you for the correction, Muthu. Yes. So this will imply, so we can take the maximum index of B to be M. So whatever remains is going to be the index of A. So that is N minus I. Then we will increase the index of A one by one. So it will be B M minus 1 dot 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 dot. The maximal index of A, that is uh, N, and then in that case it has to be M minus I. Now it's okay, right? So you just multiply both sides in such a way that you can use the induction hypothesis step. So you have uh, mm, here an raised to j plus 1 b of m minus j. Okay, so if you multiply both sides with multiply both sides with an of I, then what you will get? You will get here a n minus I, a of a n I bm plus a n minus I plus 1 a n of I b m minus 1 plus dot dot dot. You have a n I plus 1 b of m minus I is equal to 0. Just this step is crucial. So just to make you more comfortable with that, let me just write the second last term also. It's a n minus 1 a n I b of m minus I minus 1, right? It is increasing, yes. And then you have a n I plus 1 b of m minus I. Okay, and that is 0. So now how we can use the induction step? See, if you look at each of this term, so here I have b m minus j. So if I put j to be 0, then what I will get? I will get an bm is 0. So here I already have something a n minus I a n I minus 1 dot a n bm, right? And this term is 0. So this entire term is going to be 0, right? Similarly, if you pick any other term, say this term I pick, so I am subtracting I from the index m. So m minus j. So I should have I plus 1 powers of n to make it 0. So I have this, right? An I plus 1 bm minus 1 is 0. Or let's say I pick this step, this thing, then what I'm subtracting? I'm subtracting uh, 1 from bn minus from m. So this is, or if you are getting confused, let me just use a different color. Okay, it's going to be 0, right? So here it is a n minus I plus 1, and a n, and then you have a n I minus 1 b of m minus 1, right? I'm subtracting 1. Oh, that is even this is enough. I'm subtracting 1, so I need an of I plus 1, that is square. Yes, an square I should write here. It is an square and I minus 2. So this term is 0 by induction. Thus this terms gets 0. So we have 0. uh, just a moment. Oh, 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 oh. This is our induction step. All preceding steps will follow the induction hypothesis, right? Or sorry for the confusion. This term is our induction step. Okay. J equal to I term. Okay, and preceding to that, everything will go into the induction hypothesis. Okay, so I'm just writing that. So by induction hypothesis, we have everything will get cancelled out except the last term. Okay, so we have this implies 0 plus 0 plus dot 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 0 till the last term, and in the last we have an I plus m b m minus I is equal to 0. Thus it holds for j equal to I as well. This implies it is true for j equal to I as well. Thus the claim is proved. Thus the claim is. So what we have proved that for all j between 0 and m, we have this kind of term always equal to 0. A n j plus 1 b of m minus b m minus j, that is always equal to 0. Now we will use this to show that each ai is nilpotent. Okay. Okay. So, but first of all, one immediate thing is, so does the claim is justified? What does this mean? This means that an j plus 1 b m minus j is equal to 0. That is true for all 0 less than equal to j less than equal to m. Okay. So now if you put j equal to m, what you will get? So for j equal to m, you will get an m plus m b not is equal to 0, right? Yes. But we have, okay, or you I will just say multiply both sides by a naught. What you will get? You will get an m plus 1 b naught. A naught is equal to 0, right? But this is equal to 1, right? So this will implies an m plus 1 is equal to 0. and thus this is equal to 1. An is nilpotent. So till now what we have got, we got a naught is unit and an is nilpotent, but we have to show that all terms between a naught and an, these are also nilpotent. Okay, so let's set up a new claim and we will use the induction for that, because now we have the induction base step for that. So claim is a n minus k is nilpotent for all 0 less than equal to k less than equal to n minus 1. We can't go till n because that is a unit. A naught is a unit. So we will go till n minus 1. Yeah, Muthu, till here, everything okay? Muthu and Vibha Avasthi. If there is any doubt, then you can ask. Otherwise, we will move ahead. If there is no doubt, then let me proceed. So the base step is there, right? So for k equal to 0, an minus k is just an, which is nilpotent. Right? Okay. So now let us assume that let it be true for k between 0 and I minus 1. Right? So now we will establish it for k equal to I as well. Okay. So see, what we can get from this induction hypothesis. We have that a n minus 1, n minus 2, a n minus I minus 1 are nilpotents. Right? And we, using that, we show that we have already seen that we can get the terms an xn, an minus 1, xn minus 1, so on to be nilpotents. Right? This implies an xn, an minus 1, xn minus 1, an minus I minus 1, x n minus I minus 1 are nilpotents. Right? Okay. And now by 5, solution 5, we have that their sum is also nilpotent. Yeah, this is a bit tricky, but this result is very useful. So it's good to see this kind of results when you are in commutative ring setup. So this is also nilpotent. And since fx is a unit that we are given, therefore by solution 6, a unit plus a nilpotent is also a unit. So if I take this term, the negation of this term, this is also going to be nilpotent, right? If x is nilpotent, then minus x is nilpotent. So I can just write that if I subtract this term, the entire term from this, then that is also going to remain a unit. Xn minus 1 plus dot dot dot. Sorry, here it should be minus. An minus 2 xn minus 2 dot 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 minus of a n minus I minus 1 x n minus I minus 1 is a unit. But that is what that's what uh, uh, it it will be a polynomial of lower degree, because fx is a naught plus a1x plus a2x square, and now the terms after I minus 1 has already been subtracted. So we will go uh, till what? Till I only. A m minus I, right? N minus I x n minus I. The after this all terms have been cancelled due to this, right? So this is a unit that we get. So this is a unit. So see, let me just say this to be claim 1, the previous, the first claim. So this is, let's say, claim 1, and the next claim is claim 2. So in claim 1, we used that a naught is a unit, and then we proved this kind of expression, right? Now, by using that this term is a unit, proceeding similarly to claim 1, proceeding uh, in the same manner, the similar kind of calculation you need to do as in as of claim 1, we will get a of n minus I j plus 1, b of m minus j is equal to 0 for all 0 less than j less than equal to m. There we have a naught is a unit. That's why we had we subtract. See, let's have a look at claim 1 again. So here we got a n j plus 1 b m minus j. So we were subtracting 0 from n, a n minus 0 j plus 1. Here it is true for till I. So in the same like the previous one, we will just put uh, n minus I in place of n. So we will get a n minus y, a n minus I j plus 1, b m minus j is equal to 0. The same calculation you have to repeat, and you will get this thing. Okay. So now what it gives you for j equal to m, this implies a m minus j, sorry, a n minus I j plus 1 b naught is equal to 0. Again, you multiply both sides with uh, a naught, you will get that this is 0 and this thing is 1. you will get that A of n minus 1 j of n minus I, sorry, j plus 1 is equal to 0, and that will implies a n minus I is nilpotent. So we assume that it is true till a n minus I minus 1, and we prove that it is true for a n minus I as well. So thus this implies claim.
For j equal to m, you have not substituted j equal to m there.
Yes, 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 yes. I substituted in the index of B, but I didn't substitute it here. Yes, thank you. This is M, this is M, this is M. So claim 2 is satisfied. And thus, claim 2 just says that you have A1, A2, so on to AN are nilpotents. Okay. Yeah, I had some more questions, but I think it's already time. So maybe in the next lecture, I would discuss them. There was a very interesting problem that I was assuming to be to discuss, that I would complete that. But okay, let's stop here. Maybe I can just revise this proof because there are so many things that I have done here, and it's a long proof. But at least I think you can understood the statement. That's what I actually want. So what we prove that if we are in commutative ring setup, then we can explicitly define or sorry, we can explicitly see what are the units in Rx. So they are just the polynomials which has the constant term to be a unit in R, and all the coefficients of the powers of X are nilpotents in R. Okay, so you have a complete description of units in for the polynomial rings over a commutative ring. So the one implication was easy, that if you have NO to be unit and AIs to be important elements, then using the solution 5 and 6, you can get easily that fx is a unit. Now for the second, the first property, to see the first property is easy, that A0 is a unit. You just use that fx is a unit, and then you will get A0 B0 equal to 1, and that implies that A0 is a unit in R. Now for the second part, that AI is A1 dot 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 AN is nilpotent. That's the trickiest part in the proof. And for that, we first compare the coefficients of the resultant polynomial fxgx with the constant polynomial 1, and we get this, that except the first coefficient, all other are going to be 0. That's a trivial observation. And using that, we claim something like that, that a and j plus m b m minus j is equal to 0. And then we establish this claim by induction. Even see, if you just remember the claims, then you know that we are going to apply induction somehow, and then you can work out with the proof by yourself without looking at the notes, although I will upload the notes for sure. So first claim is that, and using that claim, we prove that AN is nilpotent. So now AN is nilpotent. We have the last term to be nilpotent. So what we did, we established claims such that we can use the last term as our base step. So we established the claim, claim that AN minus K is nilpotent. Now for K equal to 0, we are getting that AN is nilpotent, which is the base step. So now again, we try to apply the induction, and for that we did some computation, and then at some step, I'm just saying that using the calculations in claim 1, you can proceed in the similar way to prove this kind of expression, and put j equal to m, and you will get that an minus m, an minus I is also nilpotent. So thus the claim 2 is just satisfied, and we get that the terms a1 to an are nilpotents. Okay. So is there any doubt, Muthu? or
No doubt. Thank you very much.
okay? So this statement is very good. Means you should keep this statement, and this statement like it's used in many other theorems, and this statement if for many competition exams also, this statement is directly there in the options. So if you know this, then you can definitely see as an example also, you can see this statement in an exam. For example, you are given a polynomial, say some a0 plus a1x plus a2x square, where you are given precise values of a0, a1 and a2, and it says that whether it's a unit or not. For a particular ring, say the ring may be like z mod 4z. So you just need to check that the coefficient satisfies this property, and if the coefficients are satisfying this kind of property, then you will get that okay, uh, this is going to be the a unit in Rx. Okay, so generally this kind of statement is there in questions. For a particular ring R, they will give you a polynomial where AIs are given some values, and then they ask whether it's a unit or not. So for there, instead of doing the entire calculation, you can just use this theorem as a statement, and then you will be able to see it directly. Okay. So with that, I will stop here, and I will see you guys again on the next Friday at the same time, 6 to 8. Okay. Yes.
Thank
Thank
you.
you. Thank you, Muthu, for your interactions and for your comments. Okay. See you then. Bye.